Today we are talking about storage, indexing, and querying. There are three places in which information is stored on a computer. There is the permanent storage, composed of some HDDs or SSDs. There is the memory, also known as RAM. And finally, there is the CPU's cache. In order for the CPU to process data, it needs to query it, by which I mean that it needs to read a specific number of bytes starting from an address. Generally speaking, this can be done from either the cache or from the memory. Due to spatial limitations, the CPU's cache is very small, around 10 to 16 megabytes on modern CPUs. The CPU's cache is also split into three progressively faster portions, but that's a topic for another day. The memory, on the other hand, is much larger, ranging from 124 to 520 gigabytes on most modern mid-range servers. At the same time, the memory is dozens of times slower than the cache. The slowest level of storage, the permanent storage, is also the cheapest. Theoretically, you could find a motherboard which would support 4 terabytes of RAM, but it would cost you about 50 times as much as getting a 4 terabytes HDD. Let's assume that we are working with a dataset of daily readings from a bunch of sensors, and that it looks like this. So for every day we have an array of readings for each of our sensors. Let's say that each sensor collects a total of 10 megabytes of data each day, so a total of 250,000 readings, and we have a total of 2,000 sensors, and our dataset spans over 500 days. That is a total of 10 terabytes of data. Quite a lot to hold all of it in memory. So what we'll end up doing is storing the data onto the persistent storage. And first I want to index it using files. Let's assume that we need to do some sort of daily analysis for each of the sensors. The same choice in that regard, in terms of storing them, would be to index them by the day. So at the end of each day, we get a file with the readings from all the sensors, and we just save that file and give it the name of that specific day. When we run our analysis, we load this 20 gigabytes file into memory, and then we parse it into the individual arrays, which are, if you remember, quite small, so only 10 megabytes of data each. This means that the arrays will probably be loaded fully into the CPU's cache when we process them, making the analysis quite fast. So what we have here is essentially two ways of indexing data. We index into daily files of 20 gigabytes each when we store on the permanent storage, and we index into 2,000 separate arrays of 10 megabytes each, one per sensor, when loaded into memory. So despite us having 10 terabytes of data, the final analysis will be done on a cache-friendly amount of only 10 megabytes. This also makes the operation easy to parallelize, since nobody is stopping us from processing multiple arrays in parallel on different CPUs. And us reading from a specific file doesn't stop someone else from writing into any of the other files in parallel. Alternative methods of storage to this would be one file per sensor. This means that loading up the data for a single sensor into memory is quite fast, but loading up the data for all sensors during a specific day requires us to read through all those 10 terabytes of data. The files are also quite small at only 5 gigabytes each, so we can load them up onto smaller machines, and we can write data for other sensors into their own files in parallel with reading data from the file we care about. Alternatively, we can write one file per sensor plus day combination. So this means that looking up a specific day plus sensor combination is quite fast, and loading it in memory is quite quick. The files are very small, so 10 megabytes each. It also means that we can write almost any data in parallel with reading a file. So unless we want to update data about the specific sensor we care about on that specific day, we can modify any other file whilst reading the file we are concerned about. The problem comes with the fact that we have to store a total of 1 million files, so we have a total of 1 million indexes. This means that each time we want to read from a file, finding the file might take a while. The exact duration of this depends on the file system. It would take forever on ext3, for example, but it probably wouldn't be that slow on XFS or even ext4. And there is an easy workaround to this issue, and that is, say, having a directory structure where each day is a directory, and then that directory contains the files representing the readings for those particular sensors during that day. Lastly, storing 1 million files also means that more space is occupied on the persistent storage, since there is metadata associated with each of those files. As you can see, all the potential ways of storing this data have their advantages and disadvantages. Usually we want a structure that is flexible enough so that if our requirements change, we can do a simple and relatively quick operation that allows us to trade off one of those advantages for another. This way of storing data is a centerpiece of data engineering, and it's called a database. Before we go into looking at this problem through the lens of a database, I just want to quickly review some of the terms and concepts that the first part of this lesson went over. You've heard me use index. An index is simply a key that points towards some data in order to help you find it. Indexing a specific data set simply means creating indexes to serve as keys that help us find certain subsets of the data inside that larger dataset. When the CPU uses an address plus a length to read an array from a particular memory location, that address is essentially an index. When you create a file, that is essentially an index for the data it contains. A cache is an entity that stores data for quick access. The memory can serve as a place for caching data from the persistent storage, and the CPU's cache is obviously a cache for data that's already in memory. Finally, a query is an instruction that tells something to look for some data with certain characteristics, either by going through the data directly or by using an index. Let's take a look at our previous problem with the sensor readings in the context of a transactional database. We'll create the following schema. So we'll have a table called reading with the column sensor name, day, and readings with appropriate types. And this will yield a table of exactly 1 million rows for which we'll have 4 options as far as indexing is concerned. The first one, equivalent to the first example with the file system, would be to index on the sensor name. So we'll run a query akin to create index on sensor name. The specifics of this might differ by database. And this will create an index, or better said, a table of indices, which will look something like this. So for each distinct value of sensor name, we get an array of the row numbers that contain that value. So when we execute a query such as select all from readings, where sensor name equals sensor underline 2, instead of having to go through each of the rows, we simply get the array of row indices associated with the value sensor 2 in the index table. It should be noted that the indices are structured in such a way that looking up an equality in the data structure containing them should be faster than linear time. Depending on the type of index, this could be, for example, O log n for a B-tree index, or a 1 for a hash table index. The end result is the same. That is to say, for a large table, searching via an index is much faster than searching the table itself. The second option would be to index on the day. This would create a structure very similar to the first one, where we have each existing value of the field day associated with an array of rows. This means that querying a particular day is very fast, but asking for the readings of a particular sensor during that day requires the database to iterate through all 2000 rows associated with that day. Furthermore, if we want to ask for the readings of a particular sensor, that means the database would have to go through all 1 million rows unless we filter on a specific set of days. The third option would be to index on both day and sensor. This means that when we look up a particular day plus sensor name combination, what actually happens is that the database will get the intersection between the two arrays associated with the respective indices. Lastly, the fourth option would be to create a joint index on day plus sensor name. This is more space efficient than indexing separately on day and sensor name, and it can prove to be faster for queries that require both a filter on the day and on the sensor name. But it's quite inefficient if we ever want to get all the readings for just a single sensor or just a single day. Again, what indexing schema works for you really depends on the actual problem you are trying to solve with that data. The main advantage of using a transactional database over, say, using a file system is that you can quite easily delete and create new indexes, and you don't actually have to restructure all of your data. On to caches. Let's assume that for the purposes of this problem, you only really care about the last 2 days of reading most of the time. This means you only ever have to query a reasonably sized dataset of 40 gigabytes, small enough to host in memory on a decently sized server. What you probably want to do here is store those 40 gigabytes inside a cache where your analytics script can access it a bit more quickly. A cache in itself is just an in-memory data storage program, usually with reduced querying and indexing capacities compared to a database. Most modern caches are more similar to a directory structure that holds more files than to a transactional database. The main advantage of a cache is that it makes accessing data extremely quick, since all the data is held in memory. So usually you want to place the data that we work with a lot in a cache, and data that we only access sparingly can stay in the database. In order to accommodate for this, most caches have various forms of invalidating data. So that's to say, deleting data that is either unused or outdated. The easiest to understand and most common forms of invalidation are as follows. First, we have time to leave, also known as TTL. This means that a record, once introduced, will be deleted after a certain amount of time. In our case, since we only care about the last 2 days of reading, we could set a TTL of 2 days. So we could keep introducing a new record each day without having to worry about space, since we know that the oldest of the previous 2 days will soon be deleted based on that TTL. Second, there is usage-based invalidation. If a record keeps being used, it stays in the cache. If it's not used, it's flushed out. There are many different ways to implement this. A very basic one would be with a counter, much like the TTL. The only difference being that the counter resets to the maximum value each time that that particular data is accessed. Lastly, you can invalidate a cache due to no longer being consistent with the data source where it's gotten the data from. This makes a cache a bit more complex and adds quite a lot of overhead. We need to monitor changes in the database, since the cache needs to be made aware of these changes to flush the data and ingest new data. The exact key structure that your cache uses and the mechanism that it uses for invalidating data depends very much on the type of data you have and on your use case for said data. There are many caching softwares out there, and we'll go over some of them and how to use them in more details in further lessons. For now, I just want to sort of give you guys some definitions and lay down the basics here. I think I would be remiss if I ended this lesson without giving at least a mention to analytics databases. They differ from transactional databases in that they lend themselves to scenarios where a complex analysis is required on very large swaths of data. For example, in our sensor problem, if we wanted to unpack the arrays of readings and have one row per reading in order to run various aggregating queries on the individual readings and plug them into some formula, that's the type of database we might have wanted to use. However, analytics databases will probably require 1 or 2 videos of their own and are a bit too complex to go into right now. This video served more to familiarize the audience with some basic concepts that we'll need in the future when discussing databases, querying engines, and file systems. So hopefully it has served you well into developing a feel around what certain terms means, and hopefully it's given you an interesting view around how we store and query and find data. Until next time, have a good day.